Well, welcome back, everyone. So what we've done so far is the following. I've given you the concept of confounding. From it, we derived a definition, a working definition for confounding, what properties a confounder has to have. And we also derived a method for looking for support in the data set that a factor might be a confounder by comparing crude to adjusted analyses. Well, now I'd like to talk about one method for doing adjusted analyses. And I'm going to talk about a bunch of methods in this course. But basically, there are two general approaches for controlling for a confounder, for adjusting for a confounder. There's something called stratification. And when I was a student, this is going back some 30-something years, that's what we learned how to do. That was very common back in the 70s and the 80s, many years ago. It's not that common anymore. Now we use an alternative approach, which is based on a model, a regression model. And at the end of this course, both Marcello and I will be talking about regression models, introducing the concept of regression. And I'll be introducing how we use those models to control for confounding. But really, we're not going to cover that in detail, because to understand how a model controls for confounding requires more statistical training beyond what we're learning in this introductory course in quantitative methods. But it's something to consider for a follow-up course sometime in the future for each of you. But let's go back to this slide. I'm going to talk first about stratification. And there are two ways we can use data from stratification. We can do something called pooling, or more often referred to as weighted averaging. And that's what I'm going to show you first. We can also do something called standardization. And Marcello's mentioned standardization in his lectures. We're going to use it again in the next series of lectures when I talk about another concept, something called effect modification. We'll talk about standardization then and how it can be used to give you adjusted estimates. But for the time being, I want to focus on stratification using the notion of weighted averaging. At the very end of this course, we'll talk about regression models. I'll say a little bit about outcome regression models and say a little bit about this notion of propensity scores, which are based on regression models. More about modeling at the very end of the course. Very, very superficial, very introductory remarks at that level. But let's focus on stratification here. Stratification is a very logical way to control for confounding. One of my former teachers said you don't need a PhD in biostatistics to understand how stratification might control for confounding. It's based on a simple principle of dividing and conquering. What you're going to do is conquer confounding by dividing your data set into subgroups. These subgroups are referred to strata. So in the previous example, remember we had 2,000 people in our data set, 1,000 smokers and 1,000 non-smokers. We broke them into two subgroups, two strata, an old strata and a young strata. So that's the first thing you do. The purpose is to break people into subgroups where you no longer have confounding. So what we're going to do is we're going to stratify or subdivide our people according to categories, say males or females if I have a categorical confounder, or subranges of a continuous confounder like age. I'll put people into the young group, maybe the middle age group, and the old group if I need to have three categories. The goal is to create subgroups, create strata that are free of confounding, where everybody in the stratum is comparable, the exposed and the non-exposed people, with respect to that factor you're stratifying by. So in the previous example, I said, let's imagine all our old people are equally old. They're 82 years old. We're comparing 82-year-old smokers to 82-year-old non-smokers. There's no confounding by age in that group because whatever age does in terms of impacting our chances of getting heart disease, it's going to impact it the same in both groups because everyone's equally old. Same thing I said, let's suppose all our young people are 43 years old. Again, no confounding there. So the goal is to create subgroups that are free of confounding, which is going to be true if you have a categorical confounder. If you stratify by sex, males into one subgroup, females into the other subgroup, you can have no confounding in the male subgroup because everyone's male. But if you're stratifying by age, by putting people into strata according to subranges of age, there's a possibility of still having what we call residual confounding. You might have a subgroup which you call old, another subgroup that you call young. Say the young subgroup is everybody who's under 65 years of age. That's a pretty broad spectrum of age. It could be in that young group. Most of your smokers might be in their 50s, and most of your non-smokers might be in your 40s. So you might still have confounding left over by age, even though in that young stratum, everyone's less than age 65. Same thing in the older group. Everyone's older than 65. Maybe your smokers are in their 80s, and maybe the non-smokers are in the 70s. More likely to be the opposite, but it's possible you could still have leftover what we call residual confounding. Well, how do you get around that? By making more strata, making subranges of age that are more finely defined. You have a group of people who are 20 to 30-year-olds, another group which is 30 to 40-year-olds, another group which is 60 to 70 years old. Each group is defined by a decade of age. It's still possible within the 20 to 30-year-old group that most of your smokers could be in their high 20s and most of their non-smokers are in the low 20s. But you would not expect the risk of getting heart disease to change dramatically when you move from the early part of the early 20s to the later 20s. So the potential for residual confounding is less if you make many age strata which are narrowly defined. On the other hand, if you do that, you're spreading your data set thinner. You have more strata, fewer people to put in each of these strata. It's harder now to find a precise estimate of the association between smoking and heart disease in those strata. So there's a trade-off if you have to control for a continuous confounder. You want to have enough strata so that you have no residual confounding within each of these strata, but you don't want to have too many. So you start running out of data to fill into those many strata. Okay, so let me give you an example of a picture of what we're doing. This is top table here. Let's suppose that represents our crude analysis. That's all our 2,000 people, our 1,000 smokers and our 1,000 non-smokers. What we're going to do is divide them into two subgroups which hopefully are free of confounding. So one subgroup might be your females and the other subgroup might be your males. You have two separate 2x2 tables, one for the females, another for the males, and by definition within those subgroups, within those strata, there can be no confounding by sex. Everybody in the table that's defined by females is a female. You're comparing female smokers to female non-smokers. They're comparable with respect to sex, no confounding by sex in that table. Ditto for the males. Or one group might be young, and another group might be old if you're stratifying by age, as we did in the previous example. So that's the first step of stratification, dividing your people into subgroups where there's free of confounding. The next step is, now here's we do some calculations. Within each stratum, we measure a risk ratio, an odds ratio, a measure of association. It's in the age example, it's an age specific. We're doing one for the young people, one for the old people. And we're assuming each of these age specific or stratum specific estimates are free of confounding because the people in those subgroups are comparable, the smokers to the non-smokers. So in terms of our picture, we might divide people by young versus old, as we did before, and we measure a risk ratio, an unconfounded risk ratio among our young people to give us a valid estimate, free of confounding by age, of the effect of smoking on heart disease among young people. We do the same calculation among the old people to get an unconfounded estimate of the effect of smoking among old people. Now, that's the second step. The third step is where it becomes a little bit tricky. What we're going to do is we may combine our separate answers for separate strata into one number. That's what this idea of pooling or weighting averaging comes into play. If appropriate, and I'll talk about if appropriate in a minute, we're going to combine or pool the information from these strata together to get one common adjusted odds ratio. So if we look in our data set and we see among the young people a risk ratio that's, say, 1.49. Among the old people, it's 1.51. Those two numbers look very similar. They're both estimating a common value like smoking increases your risk by a factor of 1.5. Why don't we combine those into one single number? Why don't we take the 1.49 in one stratum, the 1.51 in the other stratum, and average together? Makes a lot of sense. If we are averaging, why don't we do something called weighting averages? If one table has more information, if we have lots of old people in our data set and very few young people, you might want to give more weight, more influence to the old table when you weight its result, when you average its result with that of the young people. That's what weighted averaging does. But notice I said if appropriate. I'm averaging. Let's go back to the beginning of this class. We talked about averages. And I talked about remembering what would happen if part of your body was burning up and part of your body was freezing over. Would it make any sense to say, on average, I'm fine? Averaging doesn't make a whole lot of sense if you're averaging different values together that represent possibly different effects. So let's suppose one of your tables gave you a risk ratio of 0.5, suggesting smoking might be beneficial. And the other tables gives you a risk ratio of 2, suggesting smoking is harmful. Does it make any sense to average the risk ratio of 2 with the risk ratio of 0.5? Maybe getting a risk ratio of 1, which is an average maybe of the 2-fold risk ratio in one group and the half-fold risk ratio in the other group. But that value 1 is not reflecting the harmful effect of smoking in one group and the potential beneficial effect in another group. So averaging doesn't make sense if the measures of association seem to be estimating different values. So the assumption behind averaging, when we do a stratified analysis, is that the effect across the strata is pretty much the same, that I'm getting different estimates from different subgroups of a common value, a common true risk ratio, as reflecting the true age-adjusted effect of smoking on heart disease. Okay, so what we're going to do is we'll end up with an adjusted value, which is an average of the risk ratios we see in these different subgroups. Now, the only problem now is how are we going to average? How are we going to determine these weights to assign to these different strain-specific results? How do we determine how much weight the risk ratio from the old people should have when we average it to the risk ratio to the young people? Well, there's a couple of different formulas around in statistics that we epidemiologists use to do weighted averaging for tables like this. The one we're going to be using is something called the Mantle Hansel weights. They are designed to essentially reflect how much information there is in a table. If a table has lots of information, it should have lots of weight when you use its risk ratio and average it with other tables that might have less information. The Mantle Hansel weights, as I'll explain in a future slide, are developed from a paper that was written by 2 individuals, Nathan Mantle and William Hansel, and they are the most commonly used weights when we do stratified analysis. Back when I was learning epidemiology, their paper was the most commonly cited paper in epidemiologic papers because those papers would use stratification using the Mantle Hansel weights. Today, as I mentioned, stratification is not used that often. Regression models are used much more often. But understanding stratification and understanding and appreciating the Mantle Hansel weights make us better consumers of stratification and later modeling as methods for controlling confounding. So let me talk a little bit about these weights and their formulas. And I'll do that in the next chunk, so I'll see you then.